Okay, tutorial 10, task 1. So this is our system and the Unity feedback loop. And following the feedback rule, we can get our closed loop system by putting it into this form. And after working it out and simplifying it, we get it in this form. And this is basically our alpha, beta, and gamma. Now finding the best settling time for a 5% overshoot for K, we aim for a 5% overshoot for working out K, like this. And these are our formulae. And since we want 5% overshoot, we put 0.05 here, and that works out to be 0.69. So plugging it back into the equation for zeta, where we set zeta to 0.69, we rearrange for K, and we have that omega n equals 2.17, which is our natural frequency. And then working out further, we get K equal to 2.21. And to find the settling time that we ended up with, we use these equations. We set K to equal 2.21, which we found before, and our natural frequency as 2.17. We plug that into the equation to find the settling time, and we get 2.67 seconds. So for task 2, this is our system, and this is the closed loop Unity feedback. And following the feedback rule, this is our closed loop system. And we have to get it into this form. And so we want to find a K for a settling time less than 4 seconds. So we will aim for 3 seconds. And we will be using these formulas to help with that. When we plug everything into the settling time equation, we have our zeta here, which has our omega and our beta, and we have our other omega over on this side. And after working this out into a calculator, we want to get 3 seconds. So we rearrange for K, and that gives us 5/3. And so to prove that this works, we're going to use these equations for the settling time and plug the K that we found in before. When we rearrange for zeta, we find that our damping ratio is 0.26. So our settling time becomes 3.05 seconds, which is what we were aiming for. And so to find the steady state error for a step input, we will use this equation where the limit when s approaches 0. And using our open loop system, as s approaches 0, we get 30. And plugging that back into the equation for steady state error, we get an error of 0.03.